Hello, I'm Gerard Wysocki, and I would like to welcome you to my laboratory. This is a Princeton University laser sensing laboratory. We are a group working on laser spectroscopy and spectroscopic sensing applications. And our work spans from fundamental laser-matter interactions all the way to applications. And today I would like to show you a few ongoing experiments, some of them at the very early stage of optics experiment, and some of them more advanced with a few systems going actually to the field for measurements that we'll be taking here on Princeton grounds to test the systems in real-world environment.
Hi guys, I'm Leng Han. I'm a postdoc collaborating with Professor Wysocki from the Geoscience Department. I am working on developing an instrument to measure the nitrogen isotopes from ocean water samples. Nitrogen cycle is really influencing the ocean's capability of taking up atmospheric carbon dioxide. So in order to measure how well the ocean nitrogen cycle is working to take up atmospheric CO2, we want to measure nitrogen isotopes in very precise region. So that's what this instrument is doing. And we use technology that was originally developed in this group called Faraday rotation spectroscopy. And I am just implementing this to work on a geoscience application.
Hi, my name's Link Patrick. I'm a sixth year in this lab, and I'm going to talk about 3 different projects. 2 of them, once again, feature Faraday rotation, and one of them features the special frequency comb lasers. But the first project incorporates breath monitoring using oxygen detection. You'd wear this on your mask, and it would come through. When I wear it, I just plug it in like this, and it will come through a variety of different measurements. And this uses wavelength modulation spectroscopy, relatively simple setup. But we move in complexity by moving on to the next project. And this is a drastic increase in complexity using both Faraday rotation and a cavity enhancement technique. The effective path length between these 2 mirrors is about 2 kilometers. And so similar to this project, this one also incorporates a magnetic field using these coils, and it creates a magnetic field which is axial to the laser. But unlike the other projects, this project uses 2 lasers, and they're both frequency combs. And not only are they frequency combs, but they're Fabry-Perot frequency combs. So this is the laser. It's very small, only 5 millimeters or less in length. And using this setup, we're able to access a variety of applications. So unlike the other project's applications, which involve high sensitivities and minimum detection limits, this project, while being also still very sensitive, is more prone to broad band measurements for large molecules that cover a large wavelength, but while being at a very fast pace. So it can take measurements in the microsecond range. So it kind of is ideal for combustion analysis. And with the incorporation of Faraday rotation technique, it would be relatively groundbreaking, which is what I'm trying to work for right now.
I'm Michael Soskine. I'm a 4th-year graduate student at Princeton, and my work is focused on laser instrumentation for optical spectroscopy in various environments. In particular, I focus on methane detection for natural gas leak mitigation, and I do that with this system right here. I do something called chirped laser dispersion spectroscopy. It enables us to determine how much methane is in any particular volume of air. So for that, we use this gimbal right here. And this gimbal is able to move in the X direction and Y direction here, so we can actually track different objects and move between different objects of interest. One of those objects is this drone. And so by flying this drone in a specified pattern, we're able to actually find and localize these plumes with high precision. What we're able to do is actually, 1, reduce the amount of greenhouse gases emitted into the environment, and 2, we're actually also able to improve the energy efficiency of energy transport in the US.
Hello everyone, I'm Jie Liu. I'm a 3rd-year grad student in Wysocki's group. The project I'm mainly working on is the project from DARPA, and the main objective for the project is to monitor multiple hazardous gas under complex urban environment. So the technique we select is called dual comb spectroscopy, and after went through several rounds in lab development, we have built a relatively compact system which can be easily fit into a minivan. And for the coming week, we will deploy the system to the field to see how the system performs under real-world situation. That's one biggest feature for the work being done in this group as well. You not only did a lot of in-lab system development, you will also try to apply your tech knowledge to real-world applications. So thanks a lot for watching the video. And if you have any questions, feel free to email us.